Okay, so sorry about yesterday. Turns out sleeping is good. Um, at least I'm staving off whatever. Um, such is life. But what I will do is, if you have the ability today, I will set up everything to. All you have to do is cut off the tops of your radishes and rinse off and dry off the roots. But if you can't, we can do it next week. Okay. But you just need to measure the weights of each of them for each set of variables. Okay. And then you can take the radish home. You can use the tops as a small salad and the radish itself. But make sure to take a couple pictures. I will have scales in there and little weigh boats and everything in the main our usual 101 room. If you cannot do that, I understand. We can do it next. Okay. And the intro that you were supposed to read, keep that fresh in your mind for next week. Okay. Because we will have class. Unless I'm dead, we will have class. And even then, we might pull a weekend at Bernie's. So, and for those who don't know that, it's a particularly disturbing 80s film where they pretended somebody wasn't dead for about a weekend and dragged a dead body around. Most places would call that desecration of the corpse. Just saying. Okay, so we are talking about ecology, and we're going to finish up a major part of it today and get the idea, a brief overview, and it is a very brief overview. Now, we are talking about population density as observing it on where they grow and why they grow this way. We can take this all the way up to populations of humans. Something stupid here. There. Okay. So when we're talking about populations of bushes, of insects, of fishes, or trees, or humans, I mean, we can look at all these different factors that can affect growth and examine what the differences, what changes can affect the overall growth of the population and how fast it'll grow, or else how much it will be impeded by certain events. Basically, food sources, of course, how quickly and available these food sources are, how many reproductions you'll have, how many offspring per reproductive event. Sometimes it's only one reproductive event. Mayflies, if you've ever been over at La Crosse in the western part of the state, there is one time a year you do not want to be around, and that's during mayfly season for about 2 weeks. And that's where insects about this long that fly, they do not bite, but it triggers something very, very deep in our psyche when you have millions of these things flying at your face. They will fly around and make drifts of maybe even 4 feet underneath street lamps and stuff like that. It'll actually cause accidents because there's so many of them. You can't stop your car. They reproduce once. So they have a very brief life above water and fly around and basically have a week to a week and a half where they mate, lay eggs, and then die. It's a brief existence. But they have one reproductive event. Now you take it all the way to us and you have multiple reproductive events potentially. In the earlier parts of this last century, people would have 9, 12, 15 kids. And most of them would survive to their reproductive age. Part of this was that you needed to have help on the farm, and it was all muscle help. We didn't have as much technology then. We were just getting into tractors and things that were motorized. and useful on the farm. Otherwise, also, we had about a 20% death rate until doctors learned to wash their hands. And then vaccinations and antibiotics came in, better medical treatments, understanding that proper vitamins and nutrients are important for fighting off infections and just survival of the child, stuff like that. Okay. So survival to reproduction was important, and how many reproduction events and how old you are before you reproduce. Now, my wife and I, after going through grad school, married early grad school, PhD land, not master's. And so we were about 24 when we got married, and we didn't have kids for 6 years. So we started at age 30. The average age is about 28 due to professional obligations, and both parents in the if you do have two parents in the workforce. But it used to be a lot younger. In European times, medieval times, it was 12 to 14. And it got up to about 19 in the 60s and 50s and 60s. And now it's 28. So we're reproducing fewer times. We are actually almost at the equality between birth and death rate right now in the US. Japan, for example, is past that, and they have a declining population. They're not birthing enough people to replace everybody that's dying. China's there for different reasons, but there's a number of places where the population is declining for many different reasons. Society, culture, economics of raising a kid. It's about $300,000 on average to raise one kid. Things like that. Now, if you're a Gen Xer, they spent significantly less on your raising and just sent you outside to go play or die. So if we're looking at all of these for humans, hey, it's kind of true. The amount of times I staggered out of a woods where we were to play with bleeding and stuff, it was, yeah. And then the bullies. Oh, well. So this is a relatively out of date, no pun intended, map of human existence, because we're starting to get more and more information about the times before. But about 8000 BC is where we have really solid evidence of agricultural societies. Before that, we have some evidence, and we're getting more evidence, but a lot of it was hunter-gatherer societies. Now, hunter-gatherer societies can't have a lot of people together because you only have so many elk in that herd that you can hunt and bring in before you depopulate the area and have to have a nomadic lifestyle, move with your food. Now, once people started having agricultural plots and raising animals in one central location for food, you could have more people together. You could afford to have more people. Just the children would survive longer. The people that are adults would survive probably longer because they weren't doing dangerous things like hunting and traveling in groups. They were able to build up a society. So the agricultural revolution was considered a major boon towards growth of populations. Now, these pieces of information here on how many people in the X or the Y-axis is on that side, sorry about it, but is in billions of people. It doesn't look like a lot. We don't have as much information. We have some records, Assyrian, Babylonian, things like that, where people were writing down on cuneiform tablets exactly how much grain they ate in a year or each day, which is kind of weird, but it kind of reminds us that there were people who were hoarders and weird people everywhere in all times. It's kind of comforting. But the estimation of how many people there was not a lot until, but even then we were were able to gain a larger population of people because we had technological information or technological advances. Agriculture, you could feed more people in a lower, closer area. But I will point out, as an infectious disease specialist, we had a problem then. Diseases that are specific to humans need humans to circulate it. And you know what what we didn't have in large groups altogether to spread something were humans. So before this, we have very few recorded and assumed human infections because there weren't high concentrations of people to keep it going and pass on. They either died or had immunity to it after that. Malaria is considered basically, as far back as we can track it, to about 8,000 to 10,000 years based on Egyptian records and such like that. We can only get it back to about that far. And then we don't really have any medical records because the only medical records we got are from people who pulled brains out of through their noses. So it's kind of shaky, but medical records from here on, we don't have anything past here. But the theory is that if you don't have humans around to spread things and amplify things, it's going to be harder to have these population-based infectious diseases. If I ever get my history of infectious disease class back up, that's co-taught with me in the history department, keep your eye out for it, because I love talking about this stuff, how history has been affected by infectious disease. It doesn't talk about it in the book, of course, but that is something. Now, it slowly grows and it doesn't look like a lot, but we're talking millions of people here. Okay. As we get more technologically advanced, and yes, they're still using bronze and such like that at certain times in here, but there's technological advances, transportation, different technologies that will help with agriculture and transporting agriculture longer distances. Some sorts of medical procedures. The mummy head. So there's a 3D printed skull on the other side of this wall here. Okay, that's a CAT scan of a mummy head. We're trying to figure out where we can give it back to. We found it in somebody's attic that gave it to us. Yeah, apparently, yeah. But we don't know who to give it back to. So we're trying to figure it out through non-destructive means. We 3D printed it, and this Egyptian young male about, well, we're assuming it's around that area, 280 BC. 19-year-old to 20-year-old has sinus surgery, evidence of holes in the sinuses where they drilled in, and surgical, dental procedures. So that medical intervention is probably helping this person live longer until he died of the ripe old age of 19. So we're going to figure out where to put that person with respect to the correct nation. We are not the London Field Museum. So we have medical interventions that are helping out with survival, and the technology is growing. We have larger amounts of people. Now, I would like to point out, there's a little dip here. This little dip is considerable when we're talking about that one on the side is 1 billion people. So the plague from the 1300s on, there were 3 main plagues. There was a Justinian plague, which was over in 380s, I believe. I'm kind of vague on that one, which we believe killed about 25 million people. We start getting better medical records about them because it's the Romans. And then about the 1330s, we have really good records of the Black Plague. And it had 3 different types: pneumonic plague, the buboes, so the bubonic plague, and then the Black Plague is where blood was pooling under the skin and everything. So it made their skin look purplish blue, like one huge bruise. They were going to die. Okay, so without medical intervention, Yersinia pestis, which is a beautifully horrible bacteria, it's designed to kill humans. It was first spread by fleas, and I could talk about this forever, so I'm not going to, but it's fascinating. There's 3 genes that caused it to survive in fleas and spread that way. 3 genes. If you take those out, it doesn't spread by flea. It could have saved everybody. 3 genes killed over 100 million people in Europe. That dip. They used to say it was 300 or 30 million. It's much, much closer. The evidence is much, much closer to 100+ million. Now, when they do any kind of building in Europe, they have to do an archaeological survey first, and they keep running into mass graves. And the mass graves are mostly from the 1280s, 1300s area, because they literally didn't have enough room to put all the plague victims individually, so they just had people tossing in all the bodies. Okay. It was a very odd time where entire villages were wiped out. Now, that by itself changed all of the human government in Europe, because they didn't have landowners anymore. We had a ton of land, but no landowners. And so we got more toward monarchies and more caste system growth and a stronger church because of that, setting up things in the future for either democracies or not democracies, but also this church versus state kind of idea, all because of Yersinia pestis. But that dip there can be examined from many different ways. Why did it happen? Close contact, lots of population to spread it. Eating more grains means more rats means more fleas. They also didn't like cats at that time and thought they were of the devil, so they killed a lot of cats, which did not eat the rats, which then meant we got fleas. It's one of those stepwise things. We had more transportation. We had Mongol horde coming across that may have brought rats all the way and fleas all the way from China, where it was first described as a disease. Now, that being said, the Chinese Empire had the best medical documentation that we have that early on. So they described this disease and how they treated it. It was really, really good records. But they also record the Mongol horde coming through. It was kind of a big thing. Seas of blood and mountains of skulls all the way across the entire continent. It's believed that it came with, but there isn't as heavy evidence. But we have spice trade routes all the way from China all the way to Europe. And there are tie-ins to bubonic plague there. So we can look at it for a number of reasons. Trade routes, higher amounts of people, cultural, how they lived, where we could have 20 or 30 people in a room half this size living. It provided really good instances where fleas could jump and bite and jump and bite and jump and bite. So there's a lot of things you can ask about, and that's just with humans with one plague. We have many, which is why I had a job for so many years and could just jump back into it. Okay, so we're not even talking about that in infectious diseases. Now, population growth has to talk about both of those, and we'll talk a little bit more about if this is a population dependent or population independent. So think about the plague in a little bit. But that last one, the Industrial Revolution. The Industrial Revolution is how we can transport people, allowing them to live longer, allowing higher populations to live longer. Canning, as in canning food and making sure it's safe to eat and transport and store long term. That was a huge change for people to survive. If you don't have that, you're more living in the moment. When there's plenty, you have plenty, but you can't store it very easily, right? So canning helped distribute the agricultural wealth to many different places and save up for those bad times. So people survive more. People were able to have better and more successful reproduction and spread across the world. So that arrow keeps going up, or that part keeps going up. So we can tie it all into these things. And that's just with humans. It's a fascinating study, history. Okay, we can also look at it in a different way. We can have a predictive model on where things will go, because we can have these age or mortality curves or age structures. And these are interesting. This will tell us a lot about the society as a whole, or that community, or that population. So it isn't just fish or anything. But well, I'll use the example of humans. How you read this, and it'll be pretty important for 1 or 2 questions on the next test. You look at this as 3 zones. Pre-reproductive age, reproductive age, and post-reproductive age. So this will change due to the organism. Humans, for example, the pre-reproductive ages are usually 0 to 19. At one time it was 0 to 14. Okay, now it's getting 0 to 25 sometimes, but pre-reproductive age is technically where they can be reproductive, and when they either culturally or biologically can. So 12 to 14, but how long they stay in this reproductive age is also key. So 40-ish to 50, depending on somebody who's really bent on having kids and is blessed that way. We can have that, and then the post-reproductive age is basically anybody past, with women, menopause, of course, where they cannot reproduce, and then males, where they traditionally do not. So age 50-ish, 60, depending on the cultural ages. Now, you have that. This x-axis is a little bit different because it isn't like a normal x-axis. This spread is how many children, how many reproducing adults, how many past reproductive adults there are. And you notice it's separated by females and males. How many are alive, first of all? How many survive to reproductive age? And you'll notice there's a couple steps. As in this area of reproductive age, how many survive to the next chunk? So we can measure that. How many reproduce? How long can they reproduce? So you're looking at this saying, okay, well, it doesn't seem like the males are dying off any faster than the females, which is surprising. And they're still getting to reproductive age. The females seem to be surviving longer post-reproductive age in this model, and surviving for a significant, not as significant amount of time actually. But we have this die off, first of all, before they're old enough to reproduce, and they have at least 2 reproduction times. Okay, so they survive that long. We have a large base, which means that there's going to be a bunch that will survive to reproduction. So this is a growth population. Now, if we have a stable population, you're going to basically replace how many you lose. So it's a little bit more than a 1-to-1 ratio given some accidents, but we don't have a lot of deaths. We don't have a lot of deaths in our reproductive age, and we're having the males dying off earlier than the females, and much more often. Okay, this is probably more realistic, honestly. But you're not making a huge amount of babies, so there's not going to be a growth in the amount of reproduction age and or the amount of people reproducing in the next couple of years or in the decades. So this is stable, barring something else coming up. Decreasing population is where you do not make up the amount of kids that you are having die here. So you have many in the post-reproductive age, and they're dying off rather quickly. Look at the depth of these cuts, these stairs. Okay, so we don't have many reproducing, and then we get into a generation that does not reproduce very much and did not survive very well. And then you're not producing as much offspring. This is a decreasing population. Think of this as Europe. Think of this as Japan, China, and unfortunately, we're right here. We're really close to getting into this decreasing population. All those are, most of those are for different reasons. Culturally, economically, sociologically, things like that. So we can predict when there's going to be a population surge, when there's going to be a population decline decades in advance. Now, telling people to go and reproduce because otherwise we're going to die out isn't taken very well. In this country, well, who's going to pay for it is the question, right? Daycare. Not everybody is around their parents and grandparents in a strong relative base to help support in an altruistic way having kids. Some people choose because of their profession not to have kids. I can only partially answer that. So about 19% of the people who had the worst COVID that survived it and got out of the intensive care, 19% were sterile, male size or male weights. It's harder to measure female reproduction, but we had over 1 million people die, and I'm saying well over that. It's at least triple that. For reasons that we could go in for wherever, but we're not testing, we're not measuring fertility rates, and we do not know the impact on our young. There are a number of studies that the American Medical Association and the American Heart Association are doing for kids 8 to 15 years old. They don't do this for accident. What we're finding is the 18 to 40-year-olds have a 40% increase in heart attacks due to COVID directly. There's little question about that. There's 30 different papers out that show this statistically over the last 3 years. So this reproductive age is having a larger cut into it. And yet we're not having multiple births here. We're not having farm families where there's 15 kids normally. We're having almost or replacing of us a 1.8 average amount of kids. So yes, we won't know how much it is because we're not testing. Yeah. I think we're going to find out a lot about the fertility rates, but also on top of that, we are going, and this is guaranteed now, that we are going to see basically a lot of heart attacks in people that are in your generation, heart events, organ problems that are usually found in 60 and 70-year-olds. And we're not looking for it because you guys are usually healthy. We're going to see it earlier and earlier. Basically, it's the fast forward in your organ age by about 20 to 30 years. And that is based on a lot of data from the last 3 years. Okay, 4 years now. We're not looking for it in your group, but the amount of different symptoms that we're going to find, we're just going to see an uptick in the amount of these symptoms. So how that affects this, I wish I could just tell everybody to start reproducing, but it's not a positive thing. I wish I could answer it better. Yeah. Hey, I did my job for King and Country. I have 3 kids, but it's not gonna. It's a drop in the bucket. Not even that. But societies can change. This is where the nature versus nurture. The nurture, the communities around us can affect how we want to reproduce. For a while, it was just 1.8 kids. Now I see a lot more people having 3 or 4 kids. But again, economics fall into it. So politically, when some people have suggested that we have free daycare for everybody, that's actually an important thing, because daycare can be $2,000 a month for 2 kids, or even 1 kid, depending on where you are, if you can find daycare at all. I personally know of people who have quit WLC not because they don't love this place, but they can't find daycare for their kid they're going to have in 9 months. That's kind of a problem. So there's a lot of sociological issues. Okay, now we can look at mortality curves. I wish I obviously could talk about this for a long time, because we've been thinking about it for a long time. I never wanted to live through one of these things. I like looking at a historical aspect, but living through something that is changing everything about our life, and we don't even know it, is yeah, it's interesting. I think we'll survive, but it's not going to be the same anything world than it was before. It's kind of like I still remember pre 9/11, before somebody took over planes and ran them into a building, buildings. I remember being able to see, we didn't have checklists or the TSA or whatever. And we could go and take kids up into the pilot and fly the airplane for a little bit, because you could see what the pilots are doing down the aisle. You can't see that anymore. So changes everything. Okay, so back on track. The mortality curves are something more about looking at how, in my case, how diseases are spread, how we can predict diseases. So West Nile virus is a mosquito-borne virus that can cause about a 1% issue here. So about 10% of people will have cold-like symptoms, but 1% of them will have very severe symptoms, death, or what's called acute poliomyelitis, where you basically have polio-like symptoms, you can't control your limbs. Some of them, most of them recover, but it's severe. We would like to predict that. Also, horses die. And if you like horses, kind of important. Now, we can predict where some of these mosquito-borne illnesses, and that's one of the lighter ones that are now coming into the area. Bone break fever is now in the south area of our nation. Dengue is called bone break fever because it makes you feel like you're having your bones break again and again and again for about 2 weeks. Also, if you get it again, you have a 10% chance of bleeding out due to hemorrhaging, kind of like Ebola. So we kind of don't want that one. But it's spread by a very specific mosquito that we now have in the US. We would like to predict when we can warn hospitals to watch out for those specific symptoms, right? So we want to know when it's going to spread, so we can look out for it in humans and possibly have better mosquito control methods at that time, so we don't have humans dying. That sounds reasonable, right? This is called epidemiology, the tracking and prediction of infectious diseases. In this case, we're looking at mosquitoes and each week and how they will show up certain populations. And this is number of cases of the specific West Nile in this case for 2018. Okay, so each week we will have a certain amount of cases of West Nile virus, and it peaks between August and September, especially in the north. For whatever reason, we didn't have as many in the south, even though we definitely know they have mosquitoes. So what we can do is start looking for the species of mosquitoes we know are in this area in May through July, basically, and start predicting when they're going to start transmitting to humans based on the peak numbers. So we can start telling the doctors to watch out for symptoms from similar symptoms and say it could be West Nile virus from July 6th all the way through probably October, depending on the year. If we have a larger population, we can have entomologists and public health officials go out and test this with mosquito traps and detect the types of mosquitoes that are there. I know this because I did that for a whole summer, part of my master's project in Milwaukee and in these southern counties. We could start predicting when there's going to be transfer over to humans because of being able to predict the growth of the mosquito populations that would transfer. So it is kind of important. Now, yeah, I can talk about the ecological side of it, but that's what translates over to humans, which some people think is the most important. So we can start predicting the populations affecting another population. Now, we can model populations by predicting, putting it to a growth model. So there's a couple terms that you need to know. Semelparity versus interoparity. Intero means repeating. Parity is talking about the reproductive events. Semel, think single. Semel, single. Single reproductive event. Intero, multiple repeating reproductive events. Humans potentially are idioparity. We are not usually semelparity. We're talking about not only the behavior of an animal or an organism, but also the ability to reproduce. So we're taking out choice and individual choice in this one. We're just looking at, say, mayflies. Mayflies will keep reproducing whenever they can, but they have a single event, so they're semelparity. So you can predict basically that they're going to double if there's nothing hindering them, nutrients, environment, predators. They'll keep reproducing until it's going to be an exponential event. It is going to double every time. And when you have a doubling, the population size can get very fast or very big very fast, from 10 in 10 reproductive cycles to 63,000, and it keeps going. So that's kind of silly though, because there are outside influences, right? Unless this is a test tube with infinite resources and no predatorial and no downstream effects from the products, this isn't real life, is it? So this still can give us some information on, okay, theoretically, if there's nothing impacting this, what would the population be without anything impacting it? Perfect conditions. Okay, let's look now at the real conditions and go, why didn't it fit this model? So it could give information on what's affecting it in theory, but that exponential growth is really not realistic, is it? What's more realistic is a logistic growth. And you want to have this carrying capacity idea in there. This carrying capacity is basically whatever environment you're in, it's the K value. And I put it here. I'm not going to have you do these calculations, don't worry. That's why I put it in small letters. But there is one specific term that I need you to know. It's an uppercase K That's a carrying capacity. You can have the population size, the change in population size, the rate of natural increase, so it takes into account that other, the exponential growth idea, what would be a perfect reproduction versus what is reality. And then you get a number based on all these variables that you can tie in on what the carrying capacity is.
So like with these five, because they like reproduce it so quickly,
Yeah.
is there like a higher like rate of mutation and like rapid mutation for there's so many generations?
That's an excellent question. Yes. Whenever you have rapid generation, you are going to have a higher rate of mutation and drift. We call it genetic drift. Now, because it's eukaryotes, we have 2 copies of everything, so it slows it down. Unless there's influx of a lot of new genetics from outside, which isn't always the case with mayflies. But yes. Now we see this a lot more with bacteria because it has 1 copy of every gene. And so you have a large genetic drift very quickly. It's sometimes termed evolution. It's more termed microevolution because you're not seeing new genes all of a sudden pop up unless they're taken up out of the environment. They don't just spontaneously show up. So yes, I like this idea, unless there's outside influences causing higher mutation rate, which you do see in some places. Selection in a closed environment or something like that. Okay, so this carrying capacity is really important. We use this in yeast, in bacteria, in a tube. We give them all the resources. They allow them to grow overnight. They grow really fast, so you have exponential growth. In this case, the number of yeast cells over hours. So this is why I like bacteria. And yeast are eukaryotes, but even bacteria grow overnight, except for chlamydia. Grow overnight, but it still has about a 36 to 48 hour life cycle. That's pretty good compared to bears, which can be decades or something like that. But things slow down. Why? Because nutrients run out. And so they have a stable population, and this stable population where it levels out means it's kind of a dark kind of suggestion where the amount dying are releasing enough nutrients so that the ones that are living can survive off of it. It doesn't last that long either. Okay, so you have this carrying capacity. In other terms, it's how many can actually live in that space. There's a number of examples of that on what can affect or cause that to stabilize. Sometimes it's just that they may have nesting amounts. Certain birds will live in trees and reproduce in trees, as in raise their young there. So if you have enough like hollow trees where you can have your choice of places to nest, that's a low population density. But if every hole of those trees is filled with a bird reproducing, and then some of them can't reproduce, that's over the carrying capacity. So it's going to level out because there's not enough reproductive events to support that entire population. Or it just might be they're able to hide from predators. So the ones who can't hide in the trees are taken up by predators. Okay, so that would be considering a density dependent growth effect. Another one is, okay, this environment has only a couple of these mice that the hawk can feed on, so it can only really support 1 hawk. But if there are a terrifying amount of mice here, where they're covering the ground like a carpet, you can have a lot of hawks and fewer of me in that area. I'm not really scared of mice, it's just that's a lot of mice. Okay, but the population density of the predators can be higher. It's a simplistic one, but we have then a problem that will limit the population, though, in those cases, where we'll have competition for resources, right? We'll have predation. Well, here's a good example. Those who can't find places to hide will get preyed upon. And then my favorite, disease. You have a higher population that can spread a disease throughout the entire population, it'll happen. By the way, if you see prairie dogs in the Southwest, stay away from them. A lot of them have the plague. We still have it here. We're one of the highest constant amounts of the plague in the world still. Outside of Madagascar, I don't understand. But the Four Corners region in the Southwest have that. And it's all in prairie dogs. So disease is a population, usually a population dependent thing. Higher population, more likely disease. So what's density independent? A fire. It doesn't care if there's a high population or not. It's going to come on through. Environmental conditions affecting this. Now, we can have physiology affecting this. We can have behaviors affecting this. Physiology, there's certain mice that have a mutation in a receptor so they don't get killed by a bark scorpion in the Southwest. They can ignore that pain and all of a sudden they have a new food source of those scorpions because they do not get affected by that toxin. Okay, that's another factor that affects physiology. Okay, I didn't get as far as I wanted to, but we'll talk about life histories and finish off ecology next time. Okay, have a great break, have a safe break. You can have those cookies, they were just there. I did not touch them.
I'm scared too. Like how have been sitting there?
At least since yesterday, I got a laptop from the and everything.
They won't, cookies are usually safe because they have a low amount of moisture in them, so it's hard to have them go bad.
It's that, it's probably we'll have to transfer it over.
You know, we had a saying in grad school, beggars can't be choosers. And in grad school, you were definitely the beggar. Oops. That wasn't supposed to show up.
They look great. I don't.